So thank you for your introduction. I am Federica Grossi. I'm a PhD student in my first year. My tutor is Professor Roberto Zanasi. The title of my research activity is Dynamic Modeling and Control of Complex Physical Systems. Just a brief outline of the contents of this presentation. First of all, I speak about power-oriented graph technique, that is the modeling technique we use in our modelization of physical systems. That is a technique based on power flows. We applied this technique to two main topics in the research. The first one is modeling of multi-phase permanent magnet synchronous motors. In particular, we see the structure of the motor, the POG scheme, the analysis of the rotor flux, and some simulations. The second topic is a new dynamic model of the tire-ground interaction in a vehicle. In particular, we see some comparisons with the Passeika approach. Then we will see the elastic element we introduce to describe the interaction of the tire with the ground. And some main points. So just a few words on the power-oriented graphs technique. This is a technique based on a block diagram, and it uses a modular structure. It is based on two main blocks, that is the elaboration block and the connection block. This technique maintains a direct correspondence between pairs of system variables and real power flows. In fact, the product of the two variables involved in each dashed line have the physical meaning of power flowing through that section. We can see the elaboration block that can store and dissipate or generate energy, while the connection block can only transform or redistribute energy. There is a direct correspondence between POG and state space description of systems. So the first topic is multi-phase motor modeling. Using a Lagrangian approach, we carried out the model of this multi-phase motor. We applied some orthonormal transformation in order to reduce the system. Here we can see the differential equations of the system in the transform space. It is a very compact way to write the dynamics of the system. We can see also the POG scheme of the considered system, and in particular, with the different colors, I point out the different kinds of block. In the left part, there is the electrical part of the motor, while in the right part, the mechanical part of the motor. These two parts are connected by a connection block, allowing an energy conversion. In particular, we deeply studied the torque vector that is very important for the torque generation. This is the formula we found for this torque vector. It has a simple structure, and it can be computed knowing the coefficients of the rotor flux Fourier series. So we made some studies on the harmonics of this rotor flux. And this led to a shaping of the optimal rotor flux in order to maximize the coefficients that generate torque. For example, as we can see from the figure, we analyzed different types of rotor fluxes. The black one is a sinusoidal rotor flux, and we can see that the red dashed one is the optimal rotor flux that allows the same torque but minimum currents and thus minimum power dissipation. The second topic I studied is the dynamical model of the tire-ground interaction. It is to say the interaction between a tire and the soil, the street, in a vehicle. We studied Passeika's formulas that are the main approach used in literature, and we pointed out some drawbacks. In particular, we pointed out the fact that Paseka's formulas, also called magic formulas, mix together the slip and skid phenomena, while they must be considered separately. So we introduced an elastic element to describe this interaction of the tire with the ground. The POG scheme in this case is represented in the figure. In the left part, there is the part related to the center of the wheel, and in the right part, the part referred to the contact point. The figure top right is showing Paseka's typical curve, and in our model we separate the skid phenomena. That is the fact that if forces exceed a skidding ellipsoid, the contact area changes dimensions, and also adherence conditions changes. While we consider in this way the slipping, that is the fact that the contact forces are kept into this skidding ellipsoid. We also made some simulations, in particular using MATLAB Simulink and SimMechanics. We also realized a model in virtual reality in order to better see our results. The scheme above is the SimMechanics scheme showing the car body, suspensions, the wheels, and the tire soil models. The figure in the right part shows the friction coefficients as function of the slip ratios. We have a good agreement with the traditional approach, but this is reached using this energetic approach. So, concluding, I presented the main line of power-oriented graph technique, and in my future work, I also will see some comparison with other energetic representations, such as bond graph and energetic macroscopic representation. For that concerns modeling, I studied multi-phase permanent magnet synchronous motors. The study will continue also with a synchronous machine and so on. And about the interaction of the tire with the ground, we want to find a clear relationship between the slip ratio and the friction coefficients. And all this work will be used for vehicle stability and control techniques such as ABS and ESP and so on. That's all. Thank you for your attention. Are there any questions?